then you can compute how Wilbur 2 behaves. Right? Because now you have a bunch of points and you're randomly shifting their x-coordinate. So it's like if you're randomly bouncing around in x and you're interested in this envelope on the left and the right, you want to know basically how many times does, let's see, I guess since I last accessed P, which is here, we didn't do that here, but in the working set bound, that's part of the deal. How many, let's see, it's sort of, if you look on the left side, it's like how many times does the max change? And you may know if you have n random numbers and you want to know how many times does the max change as I go left to right, as I take larger and larger prefixes of those n numbers, the answer is log n in expectation. Because the more points you have, the less and less likely it is for the max to change. So basically, you show the expected Wilbur 2 of a point over this randomization is theta log ti, where ti is the working set bound. And so that gives you the theorem. This gives you a lower bound of the working set bound. We have upper bounds of the working set bound, and therefore that's opt. Okay, so that's just a very quick sketch. If you're interested, check out the paper. That's unfortunately all we know what to do with Wilbur 2. But there's this other bound, Wilbur 1, which seems less good, yet we can do a lot more with it. So let me go to that. A lot easier to analyze algorithms with respect to Wilbur 1. What's Wilbur 1? We're going to fix something called a lower bound tree. I'm going to call it P because it's basically going to be a perfect binary tree on my keys. This tree never changes. That's why I say fix. It is not the binary search tree you're looking for. It is not the binary search tree that you're interested in. It's just a thing to think about. Okay? Now, for each node of that tree, like let's look at this node. I'll give the node a name, y. So here's y. There's the left subtree of y, and there's the right subtree of y. Okay, these are a bunch of keys. There's keys that are to the left of y, there's keys to the right of y. There's keys outside the subtree, we're going to ignore those. I want to look at the accesses to these keys and access to these keys and see how many times do I switch between left and right. Okay, so count number of alternations. So very similar in spirit to Wilbur 2, it's just relative to this weird tree, which is kind of arbitrary. Let's see, in the axis sequence, which is x1 up to xn, between left and right subtrees of y. So we're going to ignore accesses to y itself. We're going to ignore accesses to keys outside of y. Just look at how many times do I switch between x and y. Okay, that's a lower bound. That's the claim. It's a lower bound for the same reason. We use the independent rectangle lower bound. And the claim is if you look at these alternations, draw the corresponding rectangles. Basically, yeah. So over here we had a vertical line which corresponded to the key, and we see how many times do we cross the line. Basically the same thing over here. Except now the vertical line, there's one big vertical line that corresponds to the root node. then there's some vertical lines that correspond to this node and this node. And you're interested in the axis sequence, how many times, let's do some kind of axis sequence like this. Whatever. These are our points. And you just look at what lines are you crossing. So like this crosses the big line, so that's going to be one alternation between left and right here. Here's another alternation between left and right. Here's another alternation between left and right. Here's another alternation between left and right. And one more. Okay, so for the big line, for the root node, that's how many times you cross between left and right relative to the root. Then for the left subtree of the root, there's one crossing here. There's one crossing here. One crossing here. These are touching, but they're not satisfied, so it's okay. Claim is all these rectangles will be independent. Again, I won't prove that formally, but it's true. Okay, rough sketch. So that's Wilbur 1. It's again an independent rectangle lower bound. It's a little weird because it depends on this tree. You could choose it to be a nice perfect tree. You could choose it to be a different tree. You'll get a different lower bound each time. So of course you take the max over all trees. That will give you the biggest Wilbur 1 lower bound. We don't know much about that biggest Wilbur 1 lower bound. I guess you could ask the following open question. Is it true that for every access sequence, there exists a tree P such that Wilbur 1 is theta opt? Or is theta Wilbur 2 or something? Wilbur 2 is a single quantity. You compute it, it gives you a bound. Wilbur 1, it depends on this P. Maybe if you choose the best P for your sequence, you get the right answer. But it's definitely the case that Wilbur 1 for a fixed P is not the right answer. Recall that's easy to prove. Well, maybe we'll come back to that. Yeah, question?
So how do you construct this lower boundary? Is it just...
I'll tell you what we're going to use for... The question was, how do we construct P? You can make it whatever you want. What we're going to use is the perfect tree, which is sort of unique. It's kind of arbitrary, but it works. It has the property that its height is log n. That's all we'll need. We're going to use that to get tango trees. Other questions? All right, let me briefly mention a fun access sequence. You may recognize this sequence. This would be in-order traversal in binary. But if I take these bit sequences and read them backwards, then I get 0, 4, 2, 6, 1, 5, 3, 7. This is the number 0 through 7 in a funny order. It's called the bit reversal sequence. If you access 0, 4, 2, 6, 1, 5, 3, 7 in a perfect binary tree, it maximizes Wilbur 1. So in-order traversal, 0, 1, 2, 3, 4, 5. Whoops, no 0, 6. All right, ignore 7. There's no 7 in this tree. I do 0, 4. If you look at the root, I alternate left, right, left, right, left, right. Because the high order bit is switching every time. And so whether I go to the left of the tree here or the right of the tree is switching every time. And also if you look in any subtree, like when I'm accessing things within the subtree of 1, it alternates 0, 2. Okay, it's too small a tree to really see that happening, but it's true. And so if you do this for n bits, you get a sequence on, or k bits, n equals 2 to the k roughly. And Wilbur 1, the lower bound, is log n per guy. Because the number of alternation, every axis alternates. So if you look at a subtree, whatever the size of that subtree is, that's how many alternations there are. And so number of alternations is theta n log n, because it's the sum over all nodes of their subtree sizes. And so opt is theta n log n. We know we can achieve n log n. This is to do n axes. We know we can achieve n log n with a red-black tree or whatever, but there's actually a lower bound of n log n, meaning all binary search trees, if you're given this access sequence, doesn't matter what you're doing, you have to pay n log n, which is kind of cool. A little side effect. And that's where Wilbur's paper ended. Like, hey, cool, you can find one access sequence that is bad for everybody. But now we're going to use Wilbur 1 to get one binary search tree that's pretty good for all access sequences. Pretty good meaning within a log n factor of optimal. And this is tango trees. Would be log n competitive, online binary search trees. Why are they called tango trees? People made up all sorts of reasons, but I can tell you, because I was there, they were invented mostly on a flight from New York to Buenos Aires, which is the center of tango. I bought this T-shirt, I think, the day after. And then that week we wrote the paper, and that was tango trees. So no particular reason, but it sounds good. And always good to have a cool name. So secret is revealed. True meaning of tango trees is nothing. But we'll see. So how do they work? It's very simple. Basically, we take Wilbur 1 and we simulate it. So let me be more precise. There's one key idea, which is to look at the preferred child of a node. I'm going to say the preferred child is left. Let's see, node Y and P. It's left if we accessed the left some node in the left subtree of Y most recently. It's the right child if we access something in the right subtree most recently. So we're just looking at left and right subtree accesses. What was most recent? There's a special case in the beginning, which is you don't have a preferred child because you haven't accessed either left or right yet. So this is if no access to left or right yet. So that just happens in the beginning. Once you've touched everything, everybody will have a left or right preferred child. So this is just what was your most recent child. This is like a parent with a very short memory. It's just whichever child I most recently talked to, that is my preferred child at the moment. Okay, it's kind of like, I don't know, when you're going to job interviews, the most recent interview is the one you remember most fondly, and so you like that one the best, independent of which is the coolest. Okay, so let me draw a picture, and I guess I'm going to draw a big picture, my favorite perfectly balanced binary search tree. The 8 leaves. And so now suppose that every node has a preferred child. Let's say they all do, just because it makes a more interesting picture. I'm going to draw that with a big fat arrow. And now, what does that do? It decomposes our tree. This is the perfect tree. P is going to be perfectly balanced, log n height. Could be any log n height tree, but we'll make it perfect. And it decomposes that tree into paths. Okay, there's a path here, You just keep following parent pointers, you get a path. Not parent pointers, preferred pointers. It's also true if you follow parent pointers, you get a path, but they'll overlap each other. You follow preferred child pointers, you get non-overlapping paths. There they are. We also get these singleton paths at the leaves. Some of the leaves are in singleton paths. These are called preferred paths. Why do I care? Because so this tells me the most recently accessed element was somebody on this path. I don't quite know who. Could have been this one. And that would say, okay, this is the most recent direction we went for all of them. Let's say it's that one. Now suppose I access this node. What does that tell me? Well, if I most recently accessed left here, and now I'm accessing the right, if you look at this node, the Wilbur 1 bound goes up by 1, because I just accessed left, now I accessed right. Also, if I access this node, this guy, his Wilbur 1 bound goes up by 1, because now he's going to the right, whereas last time he went to the left. Also, this node previously went to the right and went to the left. So I get a Wilbur 1 went up because of this edge, and it went up because of this edge. In general, following non-preferred edges, I can pay for, because Wilbur 1 goes up by 1 every time I use a non-preferred edge. This is another way to state the Wilbur 1 bound. This is the cool thing. As long as I can go through a path quickly, ideally, if I could do it in constant time, this would be a dynamically optimal binary search tree. If I could instantly transport to where I need to go on a path and then jump off the path to the next path, that I can pay for. Well, I can spend constant time to do that. Then I'd be okay. I'm not going to be able to do it in constant time, but I'm going to be able to do it in log n time. I'm going to be able to jump through a path in log n time, and then figure out where I need to diverge from the path, because maybe I'm accessing this guy, jump to the next path, do that in log n time. I've got to update the path structure, because now the preferred child is to the right. It used to be to the left, so I've got to do something that will only cost log n time. If I can do that, the lower bound is the number of edges. The upper bound is number of non-preferred edges times log n. So we get a lower bound, Wilbur 1, which is going to be equal to the number of non-preferred edges. And we're going to get an upper bound through tango trees, which is going to be order number of non-preferred edges times log n. Okay, why is it log n? Because each of these paths has length only log n. So I put them in a balanced binary search tree, and it has height log n. So I take these paths, squish them into a tree. It's hard to look, I don't know which way you're squishing. It says log n depth. It's a path. I'm going to fold it into a tree so it has height only log n. Then I can jump around it in log n time. That's the idea with tango trees. We're basically done. A few details on how they work. I don't want to spend too much time on them, but let's go through some of them. So we're going to store each preferred path as an auxiliary tree, which is just, I don't know, red-black tree, let's say. What is the red-black tree sorted by? I don't have a choice. Whatever I do has to be a binary search tree among the original keys. So if I take these items and just throw them into a red-black tree, I mean, they will be sorted by whatever their x-coordinate is. So this is the max, this is the min, this is somewhere in between, this is to the left of that. So the order is a little weird. I'd really like to store them sorted by depth, but I can't do that. They are sorted by their key values. Now, what do I need to do with these auxiliary trees? I mean, the basic thing I do is a search, right? I'm searching for a key. It's a binary search tree, so I can still do a search. I can figure out, this tree gets represented as something more like this. That would be a nicely balanced version of these 4 nodes. So if I called them, I don't know, A, B, C, D, that's their sorted order. It's going to be A, B, C, D. That's also their sorted order over here. So if I search for my key, I'll figure out, oh, do I fall off here, 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 or here? Now, each of those corresponds to another path I need to visit. So if I fall off the left side of A, then I should have a pointer to this structure. If I fall off I guess these 2 are empty. Those correspond to these 2 places. If I fall off here, the right side of C, which is now here, this is going to be a pointer to my new structure, which corresponds to this one. Okay, and then this one is going to correspond to all this stuff. Well, in particular, this one. So it's a little hard to draw this picture, but you get the idea. You just rebalance each of these things, keep the pointers between the preferred paths just as they were. This is uniquely defined how to do this because it's a binary search tree. Okay, so leaves point to other, or let's call them child auxiliary trees. It's uniquely defined which ones they have to point to in order to still navigate the whole structure. So it's a weird way of rebalancing your tree. And the point is each of these red-black trees has height log n because the number of nodes in it is only log n. And that gives us the bound. Now, key thing to think about is what happens when you change. I said I have to be able to achieve number of non-preferred edges times log n. So fine, I do a log n search in here. Maybe I decide I have to go off here. Then I do a log n search in here. Okay, then maybe I have to go this way. So number of non-preferred edges was 2. I did 2, maybe 3 searches. Fine. It's going to be number of non-preferred edges plus 1 times log n. No big deal. Okay, but what? Now I have to update. Now this is the preferred edge from the root, and this is the preferred edge from this node. How do I update preferred edges? That's something to think about. So I've got a path represented by a red-black tree, and now I fall off here, and there's another path here. I need to convert this into a path that goes like this and then does this, and separately a path that does this. Okay, that's the new version. How do I do that? Conceptually, it's pretty simple. I want to cut the path here and then rejoin along there, like that. So conceptually, if things were stored by depth, this is what we call a split and a concatenate. You should know this from regular binary search trees. It's a standard exercise for like red-black trees. Given a query X, you can cut this tree into 2 halves and get 2 red-black trees, which represent everything to the left of X and everything to the right of X. Similarly, given 2 trees that are sorted like this, where all the elements are less than all the elements over here, I can concatenate them into 1 red-black tree. And all of these take log n time, where n is the number of nodes. Here, that would be log n time. In this world, it's not quite so simple because things are not sorted by depth. They're sorted by key value. But it's not so bad because, I don't know, if you look at some path and you want to say, okay, I want everything that's below, I don't know, this key value or something, then that's the same as saying, well, take everything that is within this interval of keys. So it's strictly between here and here. Let me draw this slightly. So if you look at the nodes of depth greater than d, right, I want to cut off everybody that's deeper than a particular spot in order to do this kind of change. These are equal to nodes in the subtree of that. So I've got to give it a name. Let's say I want to cut here. So I'm going to look at this node y. This is nodes in the subtree of y. All of the nodes that are below y are obviously going to have smaller depth in that path. This is nodes in a path. And nodes in a subtree are equal to nodes with keys in the min of that subtree to the max of that subtree. It's an interval. So what do? I split at min of y. I split at max of y. That gives me the interval. So here's the picture. I have a tree. I want to cut out this interval of nodes. This is like range queries, kind of, in 1D. So I split here. I split here. What I will have are the things I care about, the things to the left of it, and the things to the right of it. What I wanted was this and everything else. How do I do that? I concatenate. Maybe I should. This is y. This is in the interval min of y to max of y. So I wanted those guys. Those are the nodes that are deeper than d. I also want the nodes altogether that are less deep than d. That's these nodes and these nodes. So I concatenate these together, get one big tree that represents things with depth less than d. These are the things with depth greater than d. Okay, so I do two splits, one concatenate, and that simulates this kind of cut operation. Similarly, if I want to do a join operation, it's a constant number of splits and concatenates, and I'm done. Just dealing with the fact that things are in the wrong order here, but it's not so bad. One more thing, which is I basically describe the overall structure as a tree of auxiliary trees. In reality, we're in the binary search tree model. We can only have one tree. Not so hard, though. I mean, basically, you want one tree that represents lots of trees that are kind of pasted together. So to do that, you just mark each node that transitions from one tree to the next. So each node will say, I am the root of a new auxiliary tree, or just say, no, I'm part of the same auxiliary tree as my parent. And then you have to define these kinds of split and concatenate operations in this setting where you have a tree embedded inside a tree. But you just ignore all the nodes that are claimed to be part of another tree. Just pretend they weren't there, and it works. So a little hand wavy there. But it's kind of a tedious detail. You can stick all these trees into one tree just by marking these roots. And that's Tango trees. I already spoiled the climax, which is this log n thing, but it's pretty obvious how to get there. There's just a lot of details to actually do it. We're just taking the Wilbur 1 bound, recasting it in terms of this preferred path thing, where it's just the non-preferred edges, or the non-preferred edges are what Wilbur 1 counts, and so we can afford to spend log n time for each of them. And the paths themselves only have log n nodes, so you can search through them in log n time. Pretty easy. This also shows you why Wilbur 1 is not a good bound with a fixed tree. Because here are log n nodes. I could just sit there all day bouncing around all of them in random order. I'm definitely going to need log n time to access them, but Wilbur 1 is not changing at all. So Wilbur 1 stays constant, like 0. And I had to warm it up, but after I've touched everything, I can just sit there and bounce around these guys randomly. I've got to spend log n time to do that, but Wilbur 1 doesn't justify it for me. Wilbur 2 will go up, but Wilbur 1 with this tree is kind of lame. So this is the best Tango trees could hope to do using Wilbur 1. I would guess that Tango trees are a log factor away from optimal, though we don't know that for sure. But greedy, we're still pretty sure is good. It should be constant factor away from optimal. So I want to talk a little bit about that. There's one thing on this outline we haven't talked about. We did independent rectangles. We did Wilbur 1 and 2. We saw applications of them, in particular tango trees. One thing we haven't done is sign greedy. So let's do sign greedy. What's still left here is we have two ways to choose rectangles, independent rectangles. They're different. It'd be kind of nice to know what the best way to choose rectangles is. And we actually know that. Sign greedy. So there's two kinds of sign greedy. There's the plus sign greedy, and there's the minus sign greedy. Okay, how does plus greedy work? It's the same as greedy. You just only look at plus rectangles. Okay, remember plus rectangles and minus rectangles? So let's look at our favorite example here. With greedy, I would sweep up, and every rectangle that was unsatisfied, I would satisfy it. Now I'm going to ignore minus rectangles, only look at plus rectangles. So I see this rectangle, and I say, oh, I don't care, because that's a minus rectangle. Then I see this one and this one. Okay, I say, oh, those are plus rectangles. So I'm going to add a point here. I'm going to add a point here. Then I go up to here. I see this rectangle, which is a plus rectangle. That's bad. So I've got to add a point. I see these, this minus rectangle I don't care about. Okay, this is plus greedy. It does not satisfy the set, right? This rectangle never got satisfied. But it plus satisfies the set. If I do plus greedy, it will be plus satisfied. There's every rectangle you draw here. If it's a plus rectangle, it's got another point in it. What's kind of nice also is if you actually draw the rectangles you were satisfying. So here was one, maybe I'll use another color. There was one rectangle here. There was one rectangle here. And there was one rectangle here. That's a little awkward because they're not on the original points. So I can change them a little bit, maybe move this one down to here, and move this one over to here. Okay, you could say that those rectangles came from those points. Then this is a set of independent rectangles on the original points. Okay, maybe not totally obvious, but plus greedy will always give you, gives an independent set of plus rectangles. So it's a lower bound. It's not an upper bound because it's not satisfying the point set, but it's a lower bound. I claim it's a very good lower bound. Okay, it by itself might not be great, but you have to consider both of them. So theorem is, if I take the max of plus greedy and minus greedy, each of them is lower bound, so the max is a lower bound on optimal. Then this is within a constant factor of the biggest possible independent rectangle lower bound. And so this is the way you should choose independent rectangles. Run plus greedy, run minus greedy, take the best of the two. That will always be within a constant factor of the best independent set of rectangles. Factors like 4 or something in the worst case. So let me prove this to you. It's kind of a weird argument. I'm going to define a new quantity. Let's call this opt x, I guess. It's sort of like if you consider plus rectangles separately from minus rectangles, which is what we're doing. So I would like a point set. First, I'd like a plus satisfying point set. And then I'd also like a minus satisfying point set. And then I take their union, and I say the cost of that of the overall of that pair of plus satisfying and minus satisfying is the size of the union. So I get a bonus point if they happen to overlap. Not a big deal, just a factor of 2. Okay, so this is not a core concept, but it turns out to be basically what we're doing over here. Okay, let me give you a sequence of crazy inequalities. First one is that this opt thing is greater than or equal to size of the input. Each of these inequalities is totally obvious, but the conclusion is kind of crazy. Okay, the independent rectangle lower bound, which we proved, says that if you look at plus satisfying things, that's going to be at least size of the input plus the max number of independent rectangles. If you look at the minus satisfying things, that's also going to be at least size of the input plus maximum number of minus independent rectangles. So we already proved this, that if you look at this union, it's going to be at least size of the input plus half the overall max. Okay, so that's what we proved at the beginning of the lecture. Now, this is the best way to choose independent rectangles. Greedy, this kind of signed greedy, which is the max of the two signs, is a way to find independent rectangles. So it's only going to be worse. It's going to be smaller. So we can say is greater than or equal to half the max of plus greedy and minus greedy. Right? This was the max. So this is another way to do it, so it must be smaller. Okay. Now, greedy computes a plus satisfying assignment. So I could say, well, if you looked at the optimal plus satisfying assignment, this is something we defined at the beginning of the lecture, and the optimal minus satisfying assignment, that's only going to be smaller than greedy, because greedy is an algorithm for solving opt plus. It's can't be better than the optimum. Okay, greedy again has to be bigger than the optimum. Good. Now I just want to turn this max into a plus. So this, because the max is always at least the average. So if I take the average, which turns it into 1/4, opt plus plus opt minus. Okay, then that holds to turn the max into a plus. If I look at the optimal plus satisfying plus the optimal minus satisfying, that's only going to be bigger than this thing, because this can only save like a factor of 2 or whatever over just adding them up. But I don't even need the factor of 2 thing. I just need that if you add them up, that's only going to be worse than just counting them as the union. So we get what I call a sandwich. On the one side, we have opt x, and the other side, we have a quarter opt x. I really don't care about opt x personally. I mean, it's kind of interesting to see that it's here. But the point is, these are within a constant factor of each other. Therefore, all of these things in between are within a constant factor of each other. So in particular, this thing, max of the two greedies, is within a constant factor of this thing. This is the independent rectangle lower bound, the best one. It also tells you that opt x is basically what we're computing here. So this is weird. I'm going to draw one more picture, which is greedy versus signed greedy. Remember greedy from last lecture? Greedy says, look, I'm going to fix plus boxes, plus rectangles, and I'm going to fix minus rectangles. It does them both at the same time. Signed greedy says, look, I'm going to do the plus rectangles separately, and then I'm going to do the minus rectangles separately, and then add them up, or take the union, or take the max. Doesn't matter, constant factor. Okay, just add them separately. This one is an upper bound. It is a binary search tree. This thing is a lower bound. All binary search trees must take at least this. Are they equal up to constant factors? We don't know. That's the big question. They look almost identical. But what greedy has to deal with is sort of the interrelations. When I fix some plus rectangles, I might get new minus rectangles that I have to fix with greedy. Sign greedy doesn't have to deal with that. It's just the plus rectangles. They might make more plus rectangles, but that's all I have to deal with. It doesn't deal with the interaction between plus and minus rectangles. Seems like the interaction kind of fades away as a geometric series, and therefore these things are the same up to constant factors. But we have no way to prove that. It could be the interaction blows you out of the water somehow. That's the best we know for dynamic optimality. Maybe next time I teach this class, we'll have a final answer and it'll be constant. But that's where we are today.